Good morning, and thank you for joining us for the 63rd webinar in the Offshore Wind series, Learning from the Experts. I am Cheryl Huber, Program Manager with NYSERDA's Offshore Wind team, and it is my pleasure to be joined by today's experts, Anna Ritzen and Stefan Hartman. Before I introduce our speakers, I would like to provide a few reminders for participants and some background on this webinar series. Next slide, please. Firstly, if you are experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Experts series are available on NYSERDA's website at the address also on this slide. All participants have been muted. We will have time for Q&A following the presentation. Please use the Slido feature to submit your questions. Next slide, please. New York State is working to advance the responsible and cost-effective development of offshore wind as part of a diverse energy supply. Offshore wind is a critical component in achieving the state's energy reliability and decarbonization goals. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select Learning from the Experts speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. Please note that the views and opinions expressed in this presentation are those of the presenters. Next slide, please. It is now my pleasure to introduce Anna Ritzen and Stefan Hartman. Anna has over 17 years of experience in wind energy and project development, as well as a strong background in renewable energy and energy systems. She has achieved great results in international project management and multi-stakeholder projects and worked on multiple tenders for offshore wind. Stefan has 15 years of project management experience. He began his career in technology development for the oil and gas industry before switching to renewables. For several offshore wind projects, Stefan was responsible for the wind turbine generator scope, which covered the full project lifecycle. I will now hand things over to our speakers. Anna, I'm not sure if you're the first one to go, but it's over to you at this point.
So let me then take over for a moment while Anna is unmuting. So thanks for the introduction. Next slide, please. And Anna, please step in any moment you're unmuted.
Got it. Thanks for stepping in, Stefan. Excuse me, Cheryl. Thank you for introducing. And NYSERDA, thank you very much for hosting us. For all who are dialed in, thank you for participating. And we're looking very much forward to presenting this workshop on installation of an offshore wind farm. First of all, I would like to shortly introduce our company, which is Ventolines. We are a family-owned company based in the Netherlands, and we guide projects, renewable projects, from beginning till end, or part of that in the development and the procurement and the asset management phase and the construction phase, of course, and that's why we're here. Next slide, please. We work on onshore wind, offshore wind, battery systems, and system integration. And while we are based in the Netherlands, we also work internationally, which can be seen on this slide. So we've done several projects in the US, in Canada, the Baltics, and the Nordics, and also one outlier in Australia, which was a very nice offshore wind project as well. Next slide, please. One of the examples of what we worked on is Windpark Friesland, which is a unique project built in a lake. I also worked on this project. What was unique about this is that it's an offshore, nearshore wind farm, so built in a lake here in the Netherlands. One novel thing was that we had to construct the export cable through a frontline dam, which is quite, risky, let's say, or novel here in the Netherlands, because most of our country is below sea level. So this was a critical water barrier. We've also constructed a nature island, fit for purpose installation method, which meant normal installation vessels could not reach this site due to shallow waters and also due to the limited size of docks. So everything had to be prepared fit for purpose in order to install this wind farm. Next slide, please. On to the presentation. So for today, I will guide you through the definitions and the overview of the wind farm. We would like to make sure that everyone has the right definitions and terms in the beginning to start with, and maybe you have heard this before, but just to get everyone aligned and ensure that the terms and definitions are known. After that, I will hand the presentation over to Stefan. He will go through activity flow of the installation of a wind farm and also the typical timelines of these sequences of installation. Some generic takeaways will be presented, and after that we will go into each activity flow and present more details and a couple of practical examples per activity, and we will close with a summary, and after that the floor is yours for Q&A. Next slides. So if we look at an offshore wind farm and follow the produced electrons from left to right, on the left there's the wind turbine, the offshore wind turbine. I noted down the specifics for a typical 15 megawatt wind farm, which is now typical for the future or the near future offshore wind farms, let's say. The rotor diameter, so from blade tip to blade tip, is 236 meters, give or less, which is about 775 feet. The wind turbine will be installed on top of a foundation, which can be a monopile, so that's like a single pile, which will also be shown on the next page, and or jackets or a gravity-based foundation, or for instance a floating foundation, all depending on local siting, ground conditions, soil conditions, weather. So that's something that has to be decided upon during the development of the wind farm. The produced electricity will run through inter-array cabling. So these are the electricity cables between the wind turbines and the offshore substation, normally a 66 kV cable. And in the offshore substation, the voltage level of the electricity is stepped up in order to transport the electricity to shore. So this is normally to 220 kV, sorry. And after that, the electricity runs through the offshore export cable, so everything in the waters, and then the onshore export cable before it arrives typically in an onshore substation. So that's the little building onshore. And there again, the voltage level is stepped up in order to be able to distribute the electricity through the onshore grid. Next to that, we will talk about fabrication locations, the marshalling harbor. So this is where everything is set up before components are shipped offshore, and transport and installation vessels or time. Next slide, please. If we look at the components offshore, so this is the offshore location. We have the wind turbine, which is pictured on the left. One of the definitions of the wind turbine is the rotor, which are the blades, and the blades are connected to the hub. The hub is the front part of the nacelle. So the nacelle is the big box on top of the tower. The nacelle has the generator, inverter, and transformers, and sometimes at least, but Stefan will talk about that also. So this is all included in the box on top of the tower, and the tower is the white, let's say, pole or stick that you see. So that supports the nacelle and the blades. And the tower again is fixed on top of a foundation, and the foundation is the yellow part, and there's a lot more below sea level, which is piled in the seabed, which supports the whole construction on top. And then again, so the inter-array cables connects the different wind turbines with each other normally, and then after that to the offshore substation. And fiber optics is also installed in order to be able to communicate with the wind turbines. I think Stefan is also touching upon that. Next slide is for Stefan. I give the floor to Stefan.
Thank you, Anna. In this presentation, we'll go in depth into each of the steps, but I'd like to start with an overview to show you how these steps link together. We start with scour, then we move to foundations and inter-array cables, all installed typically by a balance of plant contractor, the BOP contractor. Potentially already termination and testing activities at this moment, but it really depends on your technical setup. Then we move to turbine installation, the wind turbine generator. But before we can install turbines, there needs to be some manufacturing of components, transport of those components, either by feeder directly to the site or preferably via pre-assembly if possible. It is noted as well that there is some manufacturing and transport, of course, for the inter-array cables and the foundations as well. But for simplicity, we show it here only for the turbines. Then the turbine contractor continues with pre-commissioning. We hand the stick back to the BOP contractor for termination and testing. Then string energization by the employer. Goes back to the turbine contractor for hot commissioning, trial runs, and finally the takeover certificate, which will be issued per turbine. Next slide, please. This slide shows how the activities of the previous slides fits in a timeline. This is just an example project of a 1 gigawatt scale project. Simplified overview, but we see here we start with the offshore substation, first some jackets, then a topside, in parallel installation of export cables. This will take roughly over a year. In parallel, we can start with the scour installation on the different locations, typically a campaign of 4 to 6 months, followed by foundation installation. Foundation installation is less sensitive to weather compared to the turbines, so this can be installed over the winter season, over the bed season, as we would call it. Duration would be roughly 6 months, depending then again on the size of your campaign and the number of positions. Followed by inter-array cables. Inter-array cables usually done in batches, potentially multiple campaigns. By that time, we reach the good seasons for turbine installation, starting the spring, summer, and potentially a little bit of the fall. However, before we can install the turbines, pre-assembly has started. There's quite a bit of preparation time for the pre-assembly site itself, and then starting pre-assembly of the components, arrival of the components. So when the first turbines are loaded out, say April, May, we start a campaign. Then depending on your setup, you can go for 1 vessel, you can go for 2 vessels. With 1 vessel, potentially you would need 2 seasons, depending on how big your site is. So you have there a difference in duration. It is noted, however, that if you go for a 1 vessel setup and you would go into the fall and you would end up in bad weather due to some delays, you get a cascading effect of delay on top of delay, potentially commissioning even be further delayed, and then you go all the way over the winter season, which is an undesirable situation. This is just the construction part. It's noted, however, that before you go into the construction, you first need to win an area, you need to get a PPA, you need to obtain permits. By that time, for the big contractors, you would consider a project, so you can negotiate your final contracts. Then you can start your engineering, do your manufacturing. So there's a whole lot of work before that, but this presentation just focuses on the offshore construction. Next slide, please. It brings me before on some generic takeaways before diving in depth. What we see there is an increase in cost going from manufacturing to pre-assembly to offshore. So if possible, we do as much as possible onshore, as much as pre-assembly onshore, to limit the exposure and the duration of the complex offshore environment. What we'll show in this presentation that we can have all nice plans on paper, but there are sometimes some technical details that influence the bigger picture. And it's really key to understand which technical details do influence the bigger picture and which don't. And we'll get to some examples here. We are working with very experienced contractors, so a lot goes really well. But if things do go wrong, we typically see elements of either interfaces that are different, use of unproven or new technology, or project-specific requirements. And then the big question is, how can you de-risk that? Next slide, please. One of the methods for that is a rehearsal of concept session, which I find personally very interactive, fun, and highly valuable. What you do is you take the contractors into a room for 1 or 2 days, and in that room, on paper, with a large layout and physical models, you build the site together. You go through each step of the detailed planning, and you visualize what is happening. And by visualizing the construction, people feel it, people taste it, and it becomes real, it becomes alive. And in that way, you increase your shared understanding, you align your assumptions, you find new risks. The sessions are too short to solve the issues on the spot, although a lot of us are engineers and we love to problem solve. We usually do that outside the session, so we identify who goes to solving issues. You would do this typically for a number of scopes, for foundation, cables, turbines. But the mantra is practice, 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 and de-risk as much as possible, and do not find out only when you're offshore. Next slide, please. That brings me then to offshore, to the first set of activities: the scour, the foundation, and the inter-array cables done by the BOP contractor. For a monopile, we start with scour protection that prevents the seabed erosion around the monopile. Placement methods really depends on the site condition, water depth, soil. Usually it can be done off the critical path, for instance with a rock dumping vessel. Then when the scour protection is installed, the foundation, the monopiles can be piled in. Monopiles are really suitable for the slightly lower water depths. You need some good soil for that. Anna touched upon that as well. If you go deeper, unfavorable soil, you might end up with jackets. There are some fun optimizations if you go for a monopile without a transition piece, which is kind of a more modern option. You first install the monopile, and then you have some additional secondary steel. The secondary steel being a main access platform, a boat landing, a main access ladder. And those can then be installed by a secondary smaller vessel. So you do the monopiles by an expensive installation vessel, and then with a less expensive vessel, you do the secondary steel. When the foundations are there, in parallel, you need an offshore high voltage station as well, not shown here in the picture, but that's a parallel scope. You have the offshore high voltage substation, and then you connect it into array cables. The closer you are from the daisy string of turbines to the offshore high voltage substation, the bigger the cables are, because there's more current going through those cables. Installation of the cables is typically on the critical path, but the burial can be done off the critical path. Next slide, please. So while the the foundations and the inter-array cables are installed, the preparations for the turbines have started. As stated, we have manufacturing of components all over the world, transported potentially with a feeder to the site to be Jones Act compliant, or if possible via a pre-assembly site. Next slide, please. In the pre-assembly site, you can have various setups, but it's very dependent on your component weight and sizes on what setup you can choose. I'll explain here an example of tower assembly. This is a UK harbour from Able UK. The top picture shows assembly of towers in big rows slightly away from the quayside. During pre-assembly, horizontal tower section is picked up, upended, becomes vertical. Then you stack 2, 3 or multiple tower sections on top of each other. You pull in a cable and you do some finishing works. And the nice thing is it's really off the critical path on the stands. Then an installation vessel arrives, picks up the towers from the quayside, it goes to the field. Now when the quayside tower stands are free, a crawler crane goes to the pre-assembled towers, picks a few up, brings them to the quayside, and when the vessel comes, they are ready. No more work to do. So a very efficient setup, very lean. However, the moment your towers get bigger, get heavier, it might not be possible to pick them up with a crawler crane, depending on the tower size, the suitability of the harbor, and the crawler cranes available. So then you live with the bottom configuration, and that is building up your towers on the quayside, on tower stands. However, there are only so many tower stands that fit within reach of the crane. So if you pick up a few towers, you start pre-assembling new towers. If you have any delays in your pre-assembly and your vessel would have a fast round trip or two, you're potentially out of towers and the vessel is waiting for the towers. And this is a typically example where your selection of turbines in a rush to get bigger and bigger turbines, for instance, there might be influences on your pre-assembly setup, which then again could influence your offshore logistics. So there's a clear link between understanding your components and your offshore logistics strategy. Next slide, please. So with the foundations installed, inter-array cables installed, we can start installing turbines. Turbine installation is done under the responsibility and by the turbine contractor. However, we need a vessel. This vessel is supplied by the employer. Sometimes you get a turbine contractor that's willing to also take up the vessel scope, but it might also be a BOP contractor or even a third party providing the vessel. So again, another fun interface. We see that installation is really sensitive for weather. Blades get get long. We have long blades. They catch a lot of wind. So those are the most critical components to install. At the same time, the offshore wind farms are moving further offshore. Hub heights are increasing. So moving further offshore, you get more wind. The hub height increases even more wind, longer blades. Difficulty to install blades. So we see that the installation duration per location increase as the turbine size increase. Then with that limited window for turbine installation we talked about, you get another input for your single versus multiple installation vessel strategy. And as a last point, we see that any location-specific components reduce your flexibility. An example here is an innovation turbine where we say, hey, let's paint one blade black or red to make sure that birds see the turbine better. That's really fun. That's something that needs to happen then in manufacturing. But that becomes now a specific set of blades that needs a specific set in the harbor, needs to go on a specific turbine potentially if you identify that. If there's any change in sequence for whatever reason, you lose flexibility. So having flexibility is something that I found to be really useful in your execution. Next slide, please. And turbines are not just installed randomly. There is some logic to the sequence. I could talk for days about this topic, but there are some considerations. For instance, monopile locations, because if your monopile sequence doesn't line up with your turbine sequence, you will get into issues as well. So you like to align them. So you need to consider potentially difficult locations to install monopiles. There might be noise limits of piling monopiles. Not all water depths are the same. So some piles you can do in some seasons, some you cannot. There might be cable crossings, for instance, with an export cable of a potentially different party. Do you want to go first? Do you want to go second? Who's then paying for the cable crossing? What is your technical risk? There are various switchgear bays at the substation where the cables are plugged in. We don't want to work next to an energized cable. So what is then the definition of working next to a cable? How close is it? Should you work on one bus bar at the same time? Another consideration is work fronts. Can you keep the work fronts in the field together? If there's an emergency, you need to get to the location in a short time. So if you spread your work fronts, you potentially need additional vessels for emergency response. So can you focus that? Can you limit durations? The shorter the campaigns are, the less exposed you are to weather, to uncertain events. So can you have, for instance, organization in blocks, a single focus campaign on the offshore high voltage substation and then finish strings instead of going string by string? A lot of considerations. At some point you decide on an installation sequence and the turbines are installed. Next slide, please. So with the turbines installed, we go to pre-commissioning. That's finishing mechanical and electrical completion, plus some additional torquing and tensioning of the bolts. Well, either torque it or tension it. Some pros and cons there as well. What is key to align with your turbine contractor is your safe state. And the safe state is the moment that the installation vessel could leave the location. So pre-commissioning is done from smaller vessels. So it's the handover from the installation vessel, leaving the location, and then finishing of the pre-commissioning works from a smaller vessel, for instance, the CTV or an SOV. That safe state requires potentially more work to be done in pre-commissioning. So aligning on the safe state makes sure that there's a best for project definition, and the installation vessel is not left on site longer than it needs to be, because typically that's the most expensive vessel in your fleet. Next slide, please. Then depending on your technical configuration, in particular your switchgear, you now need to do your termination and testing. Your switchgear can be either in your tower, it can be in a transition piece if you have it, it can be in your foundation. But the inter-array cables need to be routed, stripped and plugged into the switchgear. And in parallel, we need to fix the OTDR, just the OTDR test and the fiber optics to get also the communication ready. This then can only be done in some configurations when the tower is installed. An example there where this could lead to difficulties is for a BOP contractor wanting to go to a location for fiber optic works. To access the location with an SOV, they need to yaw away the nacelle in a safe direction. To yaw away the nacelle, you need communications. However, you don't have communications yet, because that was the work where you're going to the location for. So we see here a chicken and an egg situation. This is a typical situation that you can foresee during a rock session, you anticipate on, and you find a solution together. So now TNT is finished. We can move, TNT is finished on a string. Usually you do it string by string. We can move to string energization on the next slide, please. First big question is, what is energization? I've seen ambiguity both in speak and in contracts on the definition of both energization and grid available. Is that a substation energized? Is it the string of inter-array cables? Is it just a turbine? In my perfect world, the employer is responsible to energize then the export cable and the substation. When a string is finished, the employer will switch the switchgear, the circuit breaker, on the substation and energize the string. However, the turbine energization should be responsibility of the turbine contractor, because they installed the turbine, they commissioned it, and they have the full control. Interesting is there's a drive to limit the time from installation to starting trial runs. The sooner you can do that, the sooner you can generate pre-completion revenues. Therefore, one strategy could be, well, energize turbine by turbine, install one, energize the string, and then part of the next turbine, so you go turbine by turbine. However, again, there might be some technical constraints limiting this concept. Next slide, please. So this is a schematic. What we see here on the left is an offshore high voltage substation with an outgoing inter-array cable. We see 4 foundations installed in yellow, and we see 2 turbines installed. The first turbine, the closest to the offshore high voltage substation, is commissioned. It's fully energized and it is in trial run. At this moment, the second turbine is also installed, pre-commissioning is finished, and we would like to energize the turbine and move to hot commissioning. To do that, we need to close the disconnector on the first turbine. Next slide, please. So we want to close this disconnector, and then the string will be energized. On a 33 kV turbine, this was all fine. You could do this under voltage. However, moving to 66 kV turbines, we found out that we cannot do that anymore due to larger inrush currents, and you would get flashovers in your switchgear. Not good. So we need to do something different here if we want to energize the second inter-array cable. Next slide, please. So we first now need to open the switchgear of the switchgear, the circuit breaker towards the turbine. That means that we interrupt the trial run. Yes, next slide, please. We interrupt the trial run. Now the string can be de-energized from the offshore high voltage substation. That's what we see here, opening the circuit breaker. Now there's no more voltage on the cable. So next slide. We can move back to the turbine. On the first turbine, we close the disconnector, connect the outgoing cable. Now everything is connected. Next slide, please. We move back to the offshore high voltage substation. We energize the string. We see now the whole string is energized. Again, responsibility of the turbine, of the employer. And now the turbine contractor on the next slide can continue, re-energize the first turbine, hopefully restart the trial run, energize the second turbine, and start their hot commissioning. It is noted here that the moment that you interrupt the trial run, there are any issues in restarting it, it's the risk of the employer, so the time keeps ticking, and potentially you finish then a trial run, you run out of time, and it's deemed accepted. Alternative would be to install all turbines on the string first, then energize the full string in one go, and then energize turbine by turbine. However, then you have more time towards pre-completion revenues, but you don't interrupt your trial runs. So depending on the values and the value drivers in your project, you have here a commercial technical playing field where you could go either direction. Next slide, please. Because the fun part is we installed now 2 turbines, we install a third turbine, and we want to energize the third turbine, and we want to close the disconnector, but we cannot for the same reasons, and the whole circuit start again. Next slide, please. So having energized the string, the hot commissioning starts. There's some final tests to demonstrate that the turbine is safe, and then the turbine is put into a trial run. Trial run takes 5 to 10 days, but I've seen them as short as 3 days. Trial runs typically monitored remotely via the SCADA system. And then there's a final walkdown. This final walkdown can be done before the trial run or after the trial run. I've seen both states as well. If you do them before the trial run, you're already there on the location for hot commissioning. So right before starting the trial run, you do your final walkdown, saves one visit. However, during the trial run, you will start to sweat the turbine. It takes a number of hours to get to a steady state temperature, and only then you really start stressing your cooling systems, your hydraulics. So you could see issues, for instance, with pitch cylinders and the likes. That takes a bit of time. You see a bit of leakage. You might see that in a visual inspection, but not yet on your SCADA. So having a final walk down after the trial run could be beneficial as well. But then again, you need an additional visit, dependent on weather, on technicians. So again, a commercial technical, weighing the pros and cons. Then when we finish the trial run, the turbine will be taken over. Basically, two conditions: is the turbine performing what it should do, and is it safe? And all other items that are remaining are punch items, because the trial run really demonstrated that the turbine could run. With this very high-speed overview of activities, a simplified version, I'd like to give the floor back to Anna for a summary, and I think after that we have plenty of time in Q&A to dive into any topics you'd like to learn more about.
Yeah, so we prepared one summary slide, and while listening to your story, Stefan, there's so much more to summarize. So a takeaway is with regards to timeline, that full construction can take up to over 2 years with specialized vessels, but it all depends on your installation strategy. So do you work with one vessel? Do you work with 2 vessels? What is your expectation with regards to weather availability? So how many days or months is there a availability of good weather, let's say, to install foundations and your wind turbine? So it's quite a puzzle, let's say, to ensure installation happens as efficient as possible. And in order to do so, the mantra is prepare, prepare, prepare. So everything that can be prepared up front is little investment, but big effect. Everything that you stumble upon while being offshore already has a big impact on cost, while with the right preparation, this could potentially have been avoided upfront. The technical commercial playing field, so everything goes hand in hand with lots of contractors, so many contracts, many interfaces, many effects on commercials when potential decisions are made. So every technical concept or technical improvement could potentially have an effect on liabilities, for instance, or contracts, or delays and the effect of delays, let's say. So that has to be weighed every time over and over and over again. And last topic is the unproven technology. So innovative items that are very good for the industry to grow and to proceed and to ensure that innovations actually do happen, but it limits the flexibility in your installation sequence and even in the fabrication sequence. So that's something to keep in mind from the get-go, let's say, from the beginning of the project, that if you have an element of a single component that has to go to a particular location offshore, that limits your flexibility in your installation sequence and in your installation options. And you would like to be as flexible as possible in order to deal with any setbacks offshore. Because again, everything that can be paired up front is limited investment, big impact, and everything that needs to be taken care of offshore is more difficult with a higher impact on cost. Open for questions. We give the floor back to NYSERDA.
Thank you both very much. Appreciate all of this really interesting information, and it's quite timely for us in New York State as we see both of our contracted projects under construction and meeting a number of these milestones. So thank you very much for this information. A couple of questions have come in, and what I plan to do is just pose the question, and then you both can decide who's best suited to answer it. But I wanted to start with a clarifying question. One of our participants, or attendees, excuse me, asked for a clarification on the term employer was used throughout the presentation. Is that the offshore wind developer? Can you just describe your definition of employer?
Yeah, that's correct. An employer is the developer, and mostly in a contractual form. Typical turbine supply contract, but also the BEP contract are EPC contracts where a contractor is defined, and then you have an employer. And potentially even a third party, which is then called the engineer under FIDIC Yellow Book contract, which is an independent engineer as a separate role under the contract.
Great, thank you very much. All right, so I'll keep going with some of these other specific questions. Do low velocity currents off most West Atlantic waters diminish the need for most scour mitigation?
I don't have the answer to that one. I have to check with Stefan, but I'm not sure if he's in the call anymore. So maybe we can park that one and take it. Stefan, are you still there?
Yeah, I'm still in the call.
Ah, okay.
No, this is something more to ask to somebody of the balance of plant package. We have some colleagues who can follow up on that question. Not sure.
No problem. No problem. Thank you. Okay, can one of you please discuss how risk is managed for installation vessels? This attendee would like to know more about the developer. Do they get insurance for weather delays? What happens if the scope of work cannot be completed and the vessel must leave for other contracts, for example? So can you discuss how the risk is managed for the installation vessels?
Yeah, good question. I've seen different flavors on that as well. Basic principle is the risk goes to the party that best can take it. And as a developer, in the end, you will pay for the risk, either as a premium upfront, or you pay for it the moment that the risk mitigates. So, for instance, in weather, you could say, well, there's a standard amount of weather days already included, and if you go above, you pay for the additional time and cost. Or you can say, well, we don't include weather, we just have a P0 schedule, and any weather that comes, we pay for it. And it just depends on what deal you wanna make. Then there are two aspects, I think as well. If there are delays, depends on who's causing it. If it's weather, it's typically for the employer. However, if it's for instance, a breakdown of the installation tools by the turbine contractor, you get potentially delays on the vessel as well. So you're not then paying for the time of the contractor, but the clock keeps ticking on the installation vessel. So you might be able to make agreements back and forth, but it's understanding the different options there.
Great, thank you so much. All right, so another question here that we have is, can you share any additional perspective or advice on dense urban environments and densely used waterways for logistics, like cables and assembly? Not sure, like the design aspect of this question might be out of the scope here, but for the logistics and the planning and the waterways assembly piece, additional perspectives on when the environments are dense or more urban.
Yeah, in my experience, it makes sense to consider corridors, both for installation, but also for maintenance. We do see that the inter-array cables and the export cables are areas that are kind of the weak links in the project. So they do break down. So you do need space to go back, take up a cable, go repair it. Same for turbines. You need space around it to position your installation vessel. if you have a jack-up, you need to position your legs around your inter-array cables. So having sufficient space available is critical. It really also depends on your neighbors. How many neighbors do you have? Indeed, can you share a corridor? In Europe, in some parks, we share an offshore high voltage substation with multiple developers, with 2 developers. That's a typical Dutch configuration. So then there's already a corridor defined. But if not, it makes a lot of sense to have them.
And in addition, limitations with regards to other users of the sea, let's say, are mapped very early in the project. So if there's too many limitations to proceed with the project, you will know in an early stage of the development. After that, you try to make agreements with the other users or collaborate, indeed, as Stefan mentioned. And you take it step by step in order to ensure that during your installation phase, everything is agreed upon and clear where you will be and when you will be where, and what will be available for others and what will maybe temporarily not be available for others to use.
Thank you both. So related to that and the planning piece and timeline, there have been a couple of questions about the timeline. So typically, how much flexibility is built into a construction timeline to consider some of the things that we were just discussing?
Yeah. So yeah, float is good. So yes, you need float. So you could have a few months, for instance, from finishing the foundations. I've seen campaigns indeed where we started in October, foundations were finished in February, and turbines would only be installed in say mid-May. We would start. So there would be a few months of float. So all the activities could be just in blocks after each other. However, turbine installation would take a few months as well. So if you have delays and you're doing your turbine installation with a different vessel than your monopile installation, you might be finishing your last monopiles while you're already starting your first turbines. So there can also be overlap. But then it really depends on, do you have different vessels? I've seen projects where the same vessel would first install the monopiles and then the turbines. Well, then you're snookered. If you have source different vessels, you have more flexibility.
Great, thank you. Are there statistics on how well, I guess this question is like, how close to the schedule installation will go? Are there statistics that track this sort of thing?
Yeah, there are statistics, and I think previous presenters of companies have shown that here as well, that there are companies that track that for many fields, and you can find average duration of turbine installation, foundation installation. Typically also there's a fat tail in the risk. So if things go south, it typically takes a lot of time instead of just a little bit of extra time. So there are companies that track that data. And then depending on your risk appetite, you build a certain buffer.
Great. Specific to the timeline schematic that you were showing throughout the presentation during the different phases, there is a question here on what stages the New York State projects, what stages are they at that are under construction? I'm not sure how familiar you are with the New York projects. I can help answer that question, or happy to hear if you have an answer for this one.
No, please go ahead.
Putting it on me. So the New York State projects have monopiles installed at this point, and some of the scour protection work is happening with the ramping up of wind turbine generator installation beginning this construction season. So that might have covered a couple of the rectangles in your schematic, but I would say that it's all pre the assembly of the turbines onshore, which will be a next step. All right, great. Answered a question for you all. Sorry about that. We're taking the mic. All right, so there's a question here about energization. Would they energize offshore without energizing the transmission cable to onshore? So more about that schematic of bringing the turbines online one by one. I think the question here is maybe the sequence of that all happens offshore before it goes onshore, and related a definition of first power. Does that include just the offshore portion, or does that include like the bringing that power onshore?
You want to take it, Anna? Shall I?
You go ahead. In principle, you want to have a connection to the onshore grid.
No, correct. So there is some pre-commissioning work that can be done with temporary power. Temporary power can be provided either by diesel generators or sometimes with a big battery inside the turbine called SST, self-sustaining turbines, or island mode, depending on which contractor you talk about. So that means that the moment then that the turbine is in idling mode, there's a little bit of energy generated, and that can be used for the consumption and pre-commissioning. So then there's already some power in the turbine for the dehumidification and some tools to be used. However, the moment that you really want to put a turbine in trial run or start hot commissioning, you need a connection to the grid. We're talking about such big powers that is more than a battery or a diesel generator can generate or absorb. Even absorbing by a diesel generator wouldn't be possible. So therefore, you need a connection to your offshore high voltage substation that needs to be energized. You need a connection with your export cable to your shore station, and all those connections needs to be in place to go energize the turbines. What we usually define then as first power was then the first turbine actually exporting energy, so the first electrons flowing from the turbine to shore. That's what we call the first power.
Great, thank you so much. There's a
Also,
question about.
in addition to that, sorry, Cheryl, but one addition to that is that if you lose power, so when everything is commissioned and running, but you lose your connection to shore, that's also a big challenge for your wind farm, because your wind turbines can only be disconnected for so long. They need a little bit of power to be dehumidified, as Stefan said, and to be sure that they are running in idle, and to be sure that you can read the systems and monitor what's going on offshore. So in case of an export cable break, for instance, or another failure in your offshore or your onshore substation, that does require immediate action in order to solve the break, and in order to potentially condition each and every wind turbine with a generator in order to ensure that they can run on a little bit of external power.
That's a great point. Thank you. One of these attendees would like to know, have you started using AI in any of your processes?
I'm sure the AI is being used mainly in the operational phase, analyzing your turbines, coupling it with your digital twin, getting better prediction of your performance of your turbines, for instance, conditioning monitoring, getting a feel when your turbine will break down. So without a doubt, it is being used right there. When I was building my last two wind farms, AI wasn't that far, so it was mainly our own expertise and twinkling around in Excel. But I'm sure that it is changing as we speak.
Great, thank you. It's usually a hot topic question. I have a couple of questions here about the workforce and the workers on the vessel themselves, if you're able to answer any aspect of that related to timeline and so forth. So with regard to the installation and maintenance workers, has your team found that experienced workers are available to complete the projects? Is there a shortage? And then workers to install and maintain the projects, the skilled workers, has there been a shortage or enough of those folks to meet the timeline schedules for the projects that you've worked on?
If I focus on the turbines, which I know best, it was an issue to get sufficient people. You're working offshore. The installation vessel, the installation technicians, they work 2 weeks on, 2 weeks off rhythm. If you're further offshore, you go by SOV instead of CTV. We still had a few fields where we could have day trips with CTVs, but moving further offshore, that's not possible anymore. So you need people that are willing to have that lifestyle and have a certain technical expertise. And in particular, people with a high voltage experience, troubleshooting during hot commissioning. We sometimes called them the super ninjas, but they were very scarce. And that brings to a nice point as well, that there's also competition between the projects. So usually you as a developer, it's your project. You take pride in your project and you think it's the only project in the world, until you start realizing it's a portfolio game, and the turbine suppliers have multiple contracts running in parallel. So how do you get the technicians to your project? And that's being a good partner to them, being predictable, having good plans, making sure that indeed all the other scopes are working, and that indeed you are installing turbines, commissioning them, and taking over turbines. And then you become an attractive project, and thereby they want to put technicians on your project because they know they can finish that, take over the turbines, get rid of the liability, and get some money in. So there are a few ways to influence the scarcity of technicians as well.
Thank you. So one more question here in interest of time, and we thank you so much for answering these. So from this team's experience on wind farms, they're wondering, how did it go? What were the challenges? What went well? What are the lessons learned that you could then give some advice to other projects currently under construction?
Yeah, so my main advice would be, as we said, practice, prepare, have rock sessions, spend time on de-risking. It will really pay off. You will find some funny things that are specific to your project. Anything that makes a location specific is a potential issue if something changes. There will be mandatory things that make it location specific, like foghorns. You won't need them on any location. It might have different light requirements, but anything that is still interchangeable makes it easy is better. I've seen other projects as well that had different hub heights as an innovation. Then again, if anything happens with a tower and you want to change your sequence, you prepared your towers on your quayside, you're stuck. So the more flexibility you can have is better, because things will go wrong. And then there are long timelines for vessels, in particular manufacturing slots. So understand what you need and consider putting factory slot reservations in vessels reservations, and have some options. Anything to add, Anna?
Yeah, in addition, but that's more on the higher level PM view, that it, like, while it is a complex technical puzzle that Stefan is talking about, it's also still a people business, and you have to ensure that you have the right people in the right place. Everybody knows their responsibility and their task, let's say, or their scope of work. Upfront from the beginning, ensure that you have a good relationship with your contractors, that everybody knows the contract by heart, the limitations of the contract by heart, the interfaces of the contract, because that's where the, let's say, gray area of negotiations or discussions start. It goes again hand in hand with all the preparation that you have to execute up front. So know where you are in the whole, how do you say that, spider web of contracts and interfaces, and ensure that you have a good team and a nice atmosphere and a good energy to work on this longer term project, because it does take a long time and stuff will happen and problems need to be solved in a limited amount of time, preferably, because again, offshore is expensive time. So yeah, that would be my advice, also on top of Stefan's lessons learned from previous projects.
maybe last one to add then.
Yeah.
Contemporary records. Make sure you record what's happening. Have your own client reps. Have your own logs. You don't want to go to court or arbitration, but having your logs will help you and stay out of those situations.
Well, thank you both so very much. Really appreciate all of this information and your extra insights. We thank you for joining us for this Learning from the Experts webinar. This webinar recording and presentation slides will be available on NYSERDA's website. We also encourage you to check out past webinars in the series on NYSERDA's YouTube channel. You can register for future webinars through our events page at wind.ny.gov. Please check back soon for more information about upcoming webinars. If you would like to request a topic or speaker for this series, please email us at offshorewind@nyserda.ny.gov or fill out our Learning from the Experts survey posted on our events page. Thank you for joining us today. Thank you both, Anna and Stefan, and see you next time.